Welcome back. This is lesson 6 of Machine Learning Zoomcamp session 6, and in this lesson we will talk about random forest as a way of putting multiple decision trees together. So let's talk a bit about what we have done so far. Client comes to us, to a bank. They want to borrow some money, so they send an application. And the application contains some basic information about the item they want to buy, how much money they have, how much money they want to borrow, and so on. So then what we have is we have a decision tree here. We take this document, we extract some features from this, we send it to the decision tree, and then decision tree gives us a score, the probability that this customer is going to default or not, probability of default. And then based on that, we can take a decision whether we agree to lend some money or we reject this, yes or no. So this is what we did so far. Let's imagine for a moment that we don't have this part. So I'll just set it aside. What we have instead is we have a board of experts. We have experts here. Yeah, let's say we have 5 experts. So when somebody comes with us with an application, we forward this application to our board of experts. So each of them gets a copy. And then they independently, each of them independently on their own, decide based on this application whether they want to agree and give some money or they want to reject. So let's say this expert says yes, this expert says no, this expert says yes, this expert says yes, and this says no. So here what we have, if we have 3 decisions of yes and 2 no, so here yes wins. This is what we look at the majority vote. So whatever wins, and you can notice that we actually have 5 experts here. In this case, we cannot have a tie here. So since the majority says yes, we reply with yes, and we lend some money to the client. So this is the idea behind the board of experts. We think that 5 experts know it better than just 1 expert, and instead of relying on 1 expert, we rely on 5 of them, and if some of them disagree, then we take the majority vote. And this way we think that decisions we make are better because 5 people each has their own perspective. Yeah, so in general they should make a better decision than just 1 person. And the same idea can be applied to models. So instead of people, we can have models. So let's say this could be model G1, model G2, model G3, model G4, and model G5. Then each of these models returns some probability of default. So let me remove these decisions. Each of these models replies with a probability of default. So it could be, 0.6, 0.7, 0.3, 0.7, 0.65. And what we can do, let me move it a little bit, move it down. So what we can do now is we can take these decisions and aggregate them. So let's say we have here some sort of aggregation. From all these scores, from all these probabilities, we can take an average. So let's say if we have n experts, in our case, we have 5, but in general case, it will be n. Pi is the score that the model number I outputs, and we simply take an average. And this is what we use for aggregating the decisions. This way for aggregating multiple models can work for any model, but if instead of just taking arbitrary models, we take decision trees, then in this case, we have a random forest. Not experts here, but now you might be thinking now, why random? Why not just forest? And the reason for this is if we just take the same application, so the same set of features, and we build the same bunch of trees here, so using the same parameter, then the trees that we will have here, they will be the same. So, and then let's say we have 5 different trees that are exactly the same. Each of them outputs the same probability of default, and then the average will be the same. So it's kind of pointless. So we don't want to train the same model 5 times. So what happens in a random forest? Each of these applications, each of these features that the trees get are a little bit different. So let's say if we have 10 features in total, this tree might get 7 of them. So this tree also gets 7 of them, but a different set of features. So then this also gets 7, 7, 7, but each of them gets a different set of features. Let's take a smaller example. For example, we have a data set with, I don't know, let's say 3 features: assets, depth, and price of the item. Right, so we have these 3 features. Let's say we train only 3 models. So we can train a model using only assets and depth. So this would be our decision tree number 1. Right? Then we can train another model, but instead of using assets and depth, we can use, for example, assets and price. And then we can train yet another model, this time using depth and price. Depth and price. So this way we will have 3 different models. Let me change that. Decision tree number 2 and 3. So this way we will have 3 different models. And what we will do at the end, we will just compute the average score of all 3. P1 plus P2 plus P3. And we will do this, we will predict the average score for every client, right? So this way we have some sort of a board of experts, but instead of experts, we have models. And the idea here, of course, that features, so here, because we only had 3 columns and we wanted to train 3 models, we couldn't really select here features randomly, but the idea here is features are always selected randomly. So each model gets a random subset of features. So, and here response will be probability of default as well. We can remove this part. Yeah, so this is the main idea behind random forest. So let's train it. To use it in scikit-learn, we need to import it from the Ensemble package. From scikit-learn Ensemble, import random forest. Again, we have random forest classifier and regressor. So in this case, we need classifier. Let's say, let's create a random forest classifier. For now, we will use default parameters. We'll train only 10. So number estimators here, it's number of models we want to use. So let's keep it at 10 for now. And then the random forest fit x train, y train. So we just train a model and let's use it for predicting. So predict probability x validation. So this is how it looks like. We need only the positive column, y breadth. What we want to do now is compute the AUC score, so y validation, y prediction. So it is relatively good actually. So this is as good as our best decision tree is, and we didn't do any tuning here. So we just took the default values and we reduced the size of the model from 100. I think the default one is 100 estimators. We reduced it to 10, and we got a score that is as good as the best model, the best decision tree we had. Notice this random here. We talked that each tree gets a subset, a random subset of features. Let's say if we apply this model to see predict probability for, we can take the first row of X validation. So first row. So this is our prediction, 0.5. But if we train this model again and we apply this model again, so see now we have a different result. If we train it again, apply it again, now, yeah, so now it's the same. But I think if we keep repeating this, we will get different results. So now the probability is 0.3, and that this is a positive example. Now 0.1, it's even less. Let's see what happens now. So now it's a 0. Yeah, so we can keep trying this and we will get different results every time because there is some randomization here. So every tree gets a random subset of features. Yeah, so there is some randomization involved. And as usual, we can fix the random seed. So if we fix it at, let's say, if we set it to 1, so then no matter how many times we try, the result will be the same. So let's train it again. yeah, it's still the same. So for reproducibility, it's always important to fix the random seed for random forest model, because if we don't do this, then our results will be different each time we run this. So let's see what we can actually do with this random forest. So first, let's try to see how the performance of our model changes when we increase the number of estimators here, the number of models. So for that, what we can do, let me just clean it a little bit. So what we can do is iterate over many different values. Let's say we can go from 10 to 200. So first try it for 10, then try it for 20, and so on until we reach 200. Let me first check if we actually include 200 here. Yeah, 200 is not included, but if we do 201, yeah, so we have 200 here. So what we want to do now is we want to take this code and take this code and see how the performance of a model improves or changes when we increase the number of trees. So this will be AUC. What we also want to do now is write this to scores. So what we'll do now is append and AUC. Let's execute that. So it took some time, like less than a minute, maybe 30 seconds. I didn't measure. For you, maybe it was faster because I edited the video. So if for you it takes longer than it is taken here for me, it's because I edited the video. So yeah, now let's take a look at this course. So we have, let's create a data frame for that. Scores. So this is our data frame. Columns here would be number of estimators and AUC. So let's call it data frame scores. Yeah, take another look at this. So we see how the performance of our model changes as we increase the number of estimators. So what we can do now is we can just plot this using matplotlib. So on the x-axis, we'll have number estimators, and then on the y-axis, we'll have AUC. So again, this is number of trees. This is AUC. We see that it grows until somewhere here, so around 40 trees. I think it's 40. So it grows until 40. Is it 40? Or maybe it's actually 50. Yeah, it's 50. So it grows up until 50, but then it kind of stagnates. It doesn't really grow after 50. So here, no matter how many more trees we add after 50, the performance isn't really improving. So I think it stays somewhere 0.815, something like this, I think. So here we see that at some point it doesn't make sense to train more trees. It's enough to just have 50. And say if we have 50 experts, it's fine, but 51, 52, and so on expert do not contribute that much. Yeah, but the increase here that we have is quite rapid. So you see, and adding more experts here, more models actually helps a lot. Just like in decision trees, we can now tune our random forest model, and what we actually can tune there is exactly the same as what we tune in decision trees, because random forest consists of multiple decision trees. So the parameters we tune in random forest are the same, namely we are interested in max depth parameter and mean leaf size parameter. So let's again start with max depth parameter. What I'll do now is I'll take this code, put it here, and I will now train a random forest model for different depth parameters. So for D in 5, 10, and 15. And then for each of these depth, we will train a model using this many estimators and then set max depth to N, D. And then we keep random state here. And yeah, so what we also want to do now is add D to this course. It will take some time now. So let me, in the meantime, copy this code here. So I want to add now one more column here. So the column would be max depth. And it actually finished training. So max depth, columns, and scores. So this is how our data frame looks like. So for different values of max depth and number of estimators, we get a different AUC. Now let's plot it. So we will take this, then just do a loop for t in, copy this loop here. I'll call div subset, and then we'll take our scores and we filter scores with max depth equals to d, right? And then we plot this number of estimators on the x-axis and AUC on the y-axis, and to distinguish between different values of depth. Let's also add a legend. Let's label, well, let's just put d here, or maybe max depth equals to d. And now we need to display the legend. So, yeah, let's plot it. I think I forgot to add d here. So this is what we see. This is 5, this is 10, and this is 15. So 10 is the best one. First 10 and 15, they're relatively close, but then so for 15, it kind of stops growing. It's growing, but a little bit. And for 10, yeah, it's really, so it's doing a lot better. I think this is probably the best one. And then after that, it kind of stagnates. It's around 125. Yeah, so what we see here is that depth actually matters. So we need to set a good value for depth here. The value of 10 seems to be the best one, and because the difference between 10 and 15 is at least 1%, right? And the difference between 10 and 5 is, I think, even like maybe 2.5%, which is, I would say, quite significant. So for this data set, the value of max depth 10 seems to be the best one. So let's take a note. So 10. So we selected the best max depth parameter. Now what we want to check is what is the best mean leaf size parameter. We'll do it in the same way. So let me just copy it and paste here. So paste it here. Let's see, we can try 1, we can try 3, we can try 5, 10, I don't know, 50. Maybe this is quite a few parameters and it will take some time to train random forest, because remember, we are also trying to train many different models here, like here 200. So it will take some time, but let's try that. So max depth here is fixed. So this is the best max depth from the previous step. Here, let's say, call it S. This will be mean samples leaf S, right? And then here, instead of D to this course, we'll append not D, but S. And let's test it. Let's run it. So while it's running, I'll copy this code. So this code, I'll put it here. Now this is not max depth anymore. This is a mean samples leaf. What I want to do next is do that. So plot it. Now, instead of looping over values of D, we will loop over values of S. And you see it's still running. Oh, it finished. So now we'll loop over values of S and then select values of mean sample leaf and then plot it. And let's change the legend a little bit. So let's run it and let's run this one. I think there is a mistake, so let me just fix it real quick. Okay, so this one is 1, right? So this is, or I think it's not clear. This one and this one have the same color. So we need to fix that. Colors, black. So what we want to do is now for each of these lines define a color. And then we will loop over this and say this must be this color. So black, blue, orange, red, and let's go with gray. Sample leaf values will be this. And what we want to do now is iterate over. So for 1, it will be black. For 3, it will be blue. For 5, it will be orange. For 10, it will be red. And for 50, it will be gray. So we can do this by zipping 2 lists. And I think we already talked about zipping in one of the lessons, but let me repeat that. So let's say if we can zip this in sample leaf values with color and we execute it, we will not see anything now because this is an iterator. so it doesn't display. So if we want to display it, we need to turn this iterator into a list by doing this. And this is what we have for each value here. We get a value from here. So 1 is paired with black, then blue is paired with 3, orange is paired with 5, red is paired with 10, and gray is paired with 50. We'll do that here. So as color in zip mean sample values and colors. Yeah, here we have color. I think it should be, yes, color. And the color will be col. So let's execute that. And now we see that the gray one is 50, is the worst one, right? And these three here, this is black, orange, and blue. So this is 1, 3, and 5. And the red one is 10, is significantly worse. Not significantly, but at least 1%. Yeah, I think we can clearly see that these two are best ones. And yeah, it's not really clear what to keep here. I would actually probably go with the blue one here because it starts getting good performance earlier than others. I think also the red one, yeah, but red one then goes down. Yeah, so I would say somewhere here or maybe here in this range. I think going with blue makes more sense. It increases a little bit, but yeah, I think or maybe around 100. So yeah, around 100. This blue one with 3, it looks like it's good enough. So then let's go with min sample leaf equals to 3 as our best value. Let's retrain a model with these values. Let's retrain our random forest. And I think we said we can train it around 100 because there is no much difference between 100 and 200. Yeah, I think we can do that. So let me copy this code here. So we have the best max depth, which I think is 10. Then the mean sample leaf is 3. And let's train our model. So this is our final random forest model, which we will use at the end when we compare all different models. This is not the only 2 parameters that we can tune. There are a lot more parameters. You can check what are these parameters by going to the documentation. You can see that there is a ton of different parameters and you can read more about these parameters. So I think the most useful ones are max depth and mean sample leaf. Actually, this one and this one are pretty similar. And what is also interesting to tune is these max features. So remember the way random forest works, it doesn't get all the features, it gets only a part of features. And this feature, max features, specifies how many features each decision tree actually gets during training. And we can just put an int. So if let's say we have 10 features, we can put 7 there. It means every decision tree will get a randomly selected subset of 7 features. Or we can put a fraction here saying 75% of features, or yeah, there are different ways of doing this. You can check it here. And the other interesting one is bootstrap. So we talked about selecting a subset of features, subset of columns, and bootstrap is another way of randomization, but on the row level. So I will not go into details of what bootstrap is. You can look it up in Google, for example, but this is basically adding some randomization on the row level. So because we want our decision trees as different from each other as possible, and this bootstrap is another way of making them different from each other. Okay, and the last one probably also worth mentioning is njobs, because the process of training decision trees can be parallelized. So let's say if we have 5 models, all these models are independent from each other. So we can actually train them in parallel. And this number of jobs says how many trees we can train in parallel. So default is none, means that we are not training them in parallel, but we can put this to -1 and use all available processors. So I can quickly show you maybe here that number jobs equals -1. And then I will also open htop, which shows how many processors I have. We run this and you see that yeah, we couldn't see this, it was too fast, but here it would use all the cores they have, and then it finishes a lot faster. So this is potentially something we could do here when we train a lot of models. This will speed up the process. So go through this and see, and you can, of course, read more about these parameters. So in this lesson, what we did is we trained a random forest model. We first talked about why it's a good idea to have multiple models, why it's a good idea to have an ensemble, which is a way of combining multiple models together. We compared it with a board of experts. So it's similar. Instead of experts, we have models. And then, so random forest is a way of combining multiple decision trees into one single model, one single ensemble. Here, the decision trees have to be different from each other. So that's why we do some randomization for them, like select a different subset of columns. And then we tuned we looked how the performance of a model depends on the number of trees we have in our ensemble. And then we tuned the max depth parameter and min sample leaf parameter. And yeah, we actually wanted to train not 200, but 100. Yeah, so this is our final random forest model. And in the next lesson, we will talk about a different way of combining decision trees. So here, the trees that we train are independent from each other, so we can train them in parallel, but there is a different way of combining models when we train our models sequentially, one after another, and each model corrects the errors of the previous model. This way of combining models is called boosting, and we will talk about one particular way of boosting, gradient boosting, and we will use XGBoost, which is a library for implementing gradient boosted tree algorithm. So see you soon.